hydration reaction means you're drinking water. It is the addition of water, a short of an I here, but I'm still fine, I can still see. So you form the alcohol from alkene. Now recall that, right, given this alkene, in the presence of H plus, H2O, you get an alcohol. This is a tertiary alcohol. You can also get the similar alkene from other reagents. First one we call it oxymercuration, demercuration. So we have the mercury salt here, mercury acetate. What is AC? AC, aircon, Anglo-Chinese, acetate. Acetate means ethanoate. So we are having this group here. Okay, acetate. So this is ACO minus. Yeah? This part is AC. Acetal. Great, so this is a salt. What is a salt? A salt came from an acid-base reaction. H2O goes into this carbon, where the mercury goes into the next carbon, and the next step here, take note, this is a 2-arrow reaction, so this is step 1 and then step 2. You put in this reducing agent called sodium borohydride, which is Ra, and then you get the alcohol. Without these, you will only be stuck with the intermediate here, which is not what you want. The last step to form an alcohol from an alkene would be what we call the hydroboration oxidation. So we use alkene with our friend here, borane. We first formed this intermediate, then the next step, step 2, we added hydrogen peroxide and hydroxide to form our alcohol. So these two reactions that I just introduced to you, they are actually complementary reactions because they give a pair of alcohol of opposite addition regioselectivity. You see the first step here, it follows the normal addition of OH. But for the hydroboration, it is actually the other way of adding the OH group. Very useful in the synthesis of selective compounds. Let's continue here. So for the oxymercuration and demercuration step of this particular cyclopentene, what happens is we throw in this guy and Hg goes in first because this is an electrophile. It prefers to attack the carbon that's less hindered. Then you get a tertiary carboxyl ion. OH goes in, and then after that you throw in this sodium borohydride, it should be BH4, you get your final product. Recall that this is an anti-addition because we form the 3-member ring. We call that Hg+, so it attacks from the entire facial. Now for the second step, using the same substrate, but now we throw in the borane molecule. We add in, right, with a syn addition. Recall syn addition from the same side. That's why you see these two bonds here that just went in, newly created, they are both wedges. And then in the second stage, you throw in the second reagent that you need, peroxide, hydroxide, you get the alcohol. So that's the difference, anti-addition and syn addition. These two reactions involve both regiochemistry and stereochemistry. Bromination, as the word suggests, bro, the addition of bromine. So BrBr, that's what you use. For halohydrine, you add BrOH. So for bromination, we add Br2, we got BrBr. There's nothing much we can do. There's nothing arcane about it. There's only one way. For halohydrine formation, you add Br2 in water in excess. So this acts as a solvent as well as the reagent here. Because of the huge amount of H2O present in the system, OH compete with the Br- for the same site, the carboxyl ion. Okay, so that's the reason why you have a side product here. This is not formed at all, or you find very little amount of it, because in the first step you need to generate the more stable carboxyl ion, which is this, the tertiary one. I don't want to be going for a primary carboxyl ion. This is so bad. No. Next example, another cyclic alkene, Br. You notice something here? The Br is going for anti-addition because again Br, recall, it forms a 3-member ring forming a bromonium ion, and that's why it prefers to attack from the side that's less hindered. In this case, again, anti-addition, right, with some Regiostereochemistry. For the hydrogenation reaction, you add hydrogen into the alkene to make it saturated to form the alkane. Now, because you are using a catalyst, this is a heterogeneous catalyst. Normally, we use platinum, palladium here, or even rhodium, but these are very strong, so try to stick to these what's written on the slide with the appropriate solvent. And because this is a hard solid catalyst, so they have a surface, the mechanism is that your reagents lies on the plane, your substrate falls in, you have bonds being broken, then you rotate. Imagine a mahjong table, you shuffle, right? After that, they meet their friend, they form a bond, they interact, and then they leave the surface as a final product. So that's why the incoming groups HH will be going from the same side, so it must be a syn addition. The mechanism is like adsorption, breaking bonds, forming bonds with the surface, reaction, desorption. The last step here, desorption. You leave the surface. Why is this reaction important? Because hydrogenation is a reduction of the alkene to the alkane. All these unsaturated alkenes are present in fatty acid in vegetable oil. So when you do hydrogenation in the industry, what happens is we get margarine formed, which is a solid, yellow color solid, for better storage. Because you see that all these alkene bonds can be oxidized and the oil can become rancid easily. Very bad, and you can't keep for long. Shelf life is very short, so we want to prolong it by converting into a solid. Heard of trans fats? Trans fats, as you may have known now, trans indicates the isomeric form. When you have double bond, cis trans, so trans fats. I think the media plays it as very bad, right? How do you get trans fats? When you have incomplete hydrogenation, then you get isomerized trans fats, which increase blood cholesterol level. So bad.